discussion of Catalysis. Please. It's going to be given by one of my colleagues, Charlotte Ovesen from Toxic. Please, Charlotte.
Thank you. First of all, I would like to thank you, the organizers, for giving me the opportunity to talk here today, and Rostrup Nielsen for hiring me at Catalysis, so I was able to come here. The first slide, it is not dangerous if you know where to click this. This slide I have taken from one of Rostrup's talk, or I think from several talks that showed in the company, and I guess also several scientific talks. It sort of captures the way Rostrup thinks in science and the way he has made science, and why a lot of knowledge that has come out of it is important and useful. And it also explains why Catalysis has been able to develop competitive catalysts and new processes. It's also the way we have tried to take in this work. I'm going to talk about although on a much smaller scale. And I'm going to talk about nickel oxide reduction and new fundamental insight that have gotten into this. First of all, in this talk I'll give an introduction to steam reforming and challenges in industrial excavation, and then I will go on to talk about the reduction study that was performed to get a more detailed understanding of the effect of different supports, and also then I will propose a new model for reduction. The types of catalysts you use in steam reforming is ceramic carriers, which typically is magnesium alumina spinel, or calcium aluminate, or alpha alumina. And it's because this reaction is highly endothermic, run at high temperature, and also at high steam pressures. So they need to be very strong and inert in order to survive in steam reforming at these conditions. This is a flow sheet of a reforming plant, ammonia plant, where you see first the tubular reformer, which the gas enters at 500 and exits at around 850. Then it goes to the secondary reformer, which is operating at 1200 degrees. It's looking like this in the industry, and that's the tubular, and here you have the secondary reformer. An activation of this catalyst is done in the process gas of steam and methane, because there's not hydrogen available at the plant. So it's a challenge to be able to activate the catalyst, especially because you enter at 500 and exit at 850 in the tubular reformer. Whereas at secondary it's more easy because you have some hydrogen from the primary reformer and the high temperature. Here I show some studies that illustrates how reduction is going on in the plant. I show you here the tube, and it's how we do it in there. We have a tube for catalyst, and we have a temperature from 500 to 650 an outlet, or 850. We heat in steam, and then we introduce methane, and at some point in the bottom former part of the reactor, the methane ignites, and you get hydrogen, which starts reduction, and then by back diffusion of hydrogen, you oxidize or you reduce the nickel beneath. And you can follow that by the temperature profile, and you can see when you get reaction, you get the steam reforming, you get an endothermic dip, so you can see it moving down the bed. And when you have full reduction, you sort of have this kind of temperature profile. And it's important to get to that point, because if you do not have a proper reduction, you risk forming carbon formation because you do not have enough activity, and you also risk destroying your tubes. So sometimes when we do this thing, some catalysts are very hard to reduce, and some are easy. And why is that? We can go into the book by Rostrup, and you get some of the answers here. Here you can read about activation and reactions that can go on. When you have a nickel oxide on support, you can form a nickel alumina spinel. You can also, at lower temperature, form a surface spinel. That is if you have reactive alumina. And that is difficult to reduce. You can also make a solid solution of magnesium oxide, which is also difficult to reduce. You can have sintering. We set up a study in order to find out what is important for the types of catalysts we have. And we decided to make a study where we do it under wet conditions, since that is relevant for industrial activation. And we made some catalysts in the lab where we had magnesium alumina spinel, calcium alumina, alpha alumina, and zirconium oxide. And we also had magnesium alumina spinel with different magnesium oxide concentrations. We started into influence of calcination temperature of 550 and 850, and the techniques we had applied with temperature program reduction and in situ XRD and scanning transmission electron microscopy with EDS mapping. The first result I will show you here is for the temperature profile, same for nickel oxide on magnesium alumina spinel, in which you have not any free magnesium oxide. You see first a sharp peak, alpha peak, we call it, starting at around 500 degrees, and then you see a more broad peak at a higher temperature. And you can sort of say, is it a peak or it's more a region? And in the literature you can find that this peak is normally associated with bulk reduction of bulk nickel oxide, so nickel oxide is not affected by the support, whereas this peak up here is debated and could be reflecting support expansions. But what is the role here we also then did in situ XRD under the same conditions as the GPR in a flow of the hydrogen and water, and we could follow then the reduction of the nickel oxide and the formation of nickel. And we can see that when we reduce nickel oxide, we get the metallic nickel, that's a 1-to-1 correlation. So at all stages in the reduction, it turns into nickel. So it is pure nickel oxide we are having. And we can also see that initially it's fast reduction, which slows down, corresponding to these two peaks. And we can also go in and look at the particle sizes. Initially it's around 22 nanometers, the nickel oxide crystal size. And when you reach over here at around 500 degrees, it's 11 nanometers. So you start off by reducing the large particles, and in this region and in this region, it's smaller particles that you are reducing. And what is caused it? So that's one thing we observed. The other thing we wanted to observe or understand is the influence of free magnesium oxide. And I here show you the X-ray diffraction obtained for a catalyst which contains 4% magnesium oxide in the carrier. And this is the spectra. And first of all, here is the black one is the carrier, and the green one is the spectra for the nickel oxides on the carrier. And we also did a Rydberg analysis, so we could see that the phases we have in the carrier, magnesium oxide and spinel, and then on the support of the catalyst, we did first an analysis where we said we had two phases, magnesium oxide and nickel oxide. the separate phases, but you can see it's not a nice fit. We cannot fit the peak position, and we have this shoulder here, which we cannot fit. But if we allow the two phases to make a solid solution, as here you see the red and the green line correspond very nicely to each other. So it shows that we have both a solid solution of magnesium and nickel oxide after calcination and impregnation and calcination. And what is the effect on the temperature reduction profile? This is what I showed in this picture. It shows first the red one I showed previously, we have no free magnesium oxide. It shows the blue one with around 2% free magnesium oxide, and then the green one with 4%. And what we see is that the peak shift towards higher temperature with increasing magnesium oxide, so as this peak here, the alpha peak, turns into the beta area. And we still have this common peak here, so to say, for all the figures. So to sum up what we have learned so far in this type of picture is that if you have small particles, the low nickel content, they are hard to reduce, and that's sort of associated with the beta peak. You have large particles which are obtained if you have high nickel content. You have initially nickel that's easy to reduce, which nickel oxide will be easy to reduce, which resembles sort of bulk nickel oxide, and you have a part that is difficult to reduce, which is interacting with the substrate. We also see that magnesium oxide increasing content, it shifts the reduction to temperature to higher temperatures, and is associated with this solid solution of magnesium and nickel oxide, and associated with support interactions. The next things we decided to study was the effect of calcination temperature, and here I show you both the 450 profile and the one obtained at 850. And this is for the carrier without magnesium oxide. You see a drastic change in the peak, and you obtain another peak. And this peak is in the literature associated with nickel aluminum reduction of nickel aluminum SPL. We also asked ourselves how is it with the magnesium oxide, is it influenced by that? And here we see the profiles for the three catalysts, 0, 2, and 4 weight percent magnesium oxide, and we see that they sort of coincide. So this shift in the peak position is not strongly dependent on magnesium content, and it's another effect we are looking for. But could it be formation of nickel alumina SPL? This question we then try to answer by looking at the XRD spectrum. And here the blue line is the spectrum for the 450 cosine sample, and the red is for the 850 cosine sample. And you can see they almost coincide. And the XRD spectrum tells us we have nickel oxide. It's not nickel aluminum SPL. So it's nickel oxide and low catalyst. So it's not supported by the anticipation that it has nickel. Also, if you look at the integrated concentration of nickel oxide, you see that you get metallic nickel, also for the catalyst inside at 50. So we start up here to reduce at around 700, and you see as you lose nickel oxide, you get metallic nickel. So we took this sample that we have stopped reducing here at around 750, and so after the question is a surface protection layer. And we took it and made a scanning transmission electron microscopy image. And here we see that we both can see reduced nickel particle and we can see unreduced nickel particle. as was apparent in that XRP spectra. And if we then make a high-angle annular dark field emission analysis of this spectrum, we can see then here the particle, we can see the alumina, magnesium, nickel, and oxide. So we see the nickel particle, and we see we have alumina on the surface of this nickel particle, and especially here at the edge, which when we look, this picture is taken looking on the side, and we see when we do an analysis of the concentration, we have an increased concentration of alumina at this edge. And to illustrate it a little further, we took and made a line scan in this area shown here, and this is the corresponding spectrum. And if you see here the line scan from the surface and into the particle, you see you have an increased concentration of alumina, whereas you have only a little inside here. So the line supports that you have the particles surrounded by a thin alumina layer of the clear alumina layer. And it supports that you have formed a surface nickel and manganese. And this is the reason why it's difficult to reduce. This is only for the magnesium aluminum that we see that. Here I have a temperature profile for a number of catalysts for the calcium aluminate, those 450 and 850, and we see also for the calcium aluminate we have a high temperature peak. And for alpha aluminate we also have this high temperature peak, but for zirconia oxide we do not have this peak. So all alumina containing catalysts have this phase, but alpha alumina, you can see it has a little peak also in the alpha region, so it's not fully nickel aluminum scale, and it's probably more difficult to make on this carrier. And zirconium has none of this peak, which is supported by alumina. So in situ XRP also support this. Here is shown both for the 450 and for the 850, and we see this that when we reduce nickel oxide, we get nickel 1:1. You see it for the calcium aluminate here also, and you see it for the alpha alumina, and you see it for the zirconium oxide. There are many information in this, and you can see that the rate of reduction is a little different depending on the support, but they all have this highly overlay that is not difficult to reduce. So this institute data is fully consistent with the TPI data. And finally, then I go to the proposal of a reduction model, and this is sort of the picture we have. Nanoparticles of nickel oxide with no support interaction produces around 400 to 450 gluons, and is what we imagine is large nickel particles and the top part of the surface interaction with the support contributes to higher reduction temperature, and you can imagine that for the 450 you have alumina, perhaps creeping a little alumina items onto the catalyst, and that can also make it harder to reduce. And for small particles, you can have alumina also makes it harder to reduce. For the 850, you have simply formed this layer of nickel alumina spinel, so you have to reduce that before you can reduce the nickel oxide. And then if you have the magnesium oxide, you can also make a solid solution with nickel oxide, magnesium oxide. So what we have learned in this study is we have been able to propose a model for nickel oxide reduction and different support, and formation of a surface generator over the center of typical steam reforming catalyst. The calcination of typical steam reforming catalyst should therefore be done at the lowest possible temperature. And when we do on-site activation, we should be very careful not to steam at too high temperature, because then you form this over there and it's very difficult to reduce, and you may have problems getting good reduction and problems with high getting enough activity and avoid compensation. So with this I will conclude, and thank you for your attention.
Thank you very much. Questions? Comments? Yes?
Yeah. I noticed that for the hydrogen TPR, you use hydrogen helium plus steam. So but usually when people try to do the TPR, hydrogen TPR, they use hydrogen argon. But what's the special reason to use hydrogen helium plus water? Because the thermal conductivity between hydrogen and helium is the same.